Welcome to this explainer. Today, I'm going to act as your patient tutor. We're going to break down the complex anatomy of centrifugal pumps step by step so you can fully master how and why they fail. And listen, we are going to take this one step at a time, and I am not moving on until the logic of each part is absolutely crystal clear. Why? Because to successfully fix a machine, you have to intimately understand it first. A single failed pump can shut down a whole factory floor or stop a chemical process dead in its tracks. The stakes are incredibly high. And honestly, guesswork just isn't an option. Here is our roadmap for today. 1. Meet the centrifugal pump. 2. Powering up with the motor. 3. Transferring power via the shaft coupling. 4. Pumping action with the impeller and volute. 5. Protection through seals and bearings. And finally 6. Mastering the failure tree. Let's jump right in. Section 1. Meet the centrifugal pump. Like I said, to understand how something breaks, we first must intimately understand how it's actually put together. Now, this beautifully detailed diagram by Ajay Kumar Vipili is going to be our master failure tree today. It shows us exactly where things can go wrong, simply by showing us where everything belongs. Take a really good look at this layout. This cross-section is our playground. And hey, don't worry if it looks like a complicated mess of metal right now. By the end of this lesson, you are going to know this machine inside and out. The absolute foundation of diagnosing failures is understanding the anatomy. Before we can even start talking about vibrations or leaks or sudden pressure drops, we have to establish a rock-solid mental map of the hardware itself. Think of it this way. You can't diagnose a sports injury if you don't know the bones and muscles, right? Are you with me? Excellent. Let's start mapping it out. Section 2. Powering up the electric motor. Every journey of power has a starting point, so let's start at the absolute source of the energy. Notice the large blue cylinder over on the far right of the unit? That's the electric motor. This is the muscle. It generates all the kinetic energy for the entire system. Without this component spinning, absolutely nothing happens. But keep in mind, because it does all the heavy lifting, it's also our very first major point of potential failure. If this motor overheats because of poor ventilation, or if it experiences an internal electrical short, the whole process stops dead. It's the engine, and it demands our respect. So here is the absolutely crucial four-step path of energy. First, the motor spins, generating that raw rotational force. Second, the coupling transfers that spin across the physical gap. Third, the long shaft turns the impeller inside the casing. And fourth, the impeller aggressively moves the fluid. If any single step in this sequence fails, the energy transfer stops and the pump is basically just an expensive paperweight. I want you to really visualize that kinetic energy moving from right to left. Do you have that sequence locked in? Good, because I promised not to move on until you did. Let's examine that crucial second step. Section 3. Transferring power, the shaft coupling. Let's make sure we understand this first transfer step before we even look at the liquid end. How does the motor's energy actually get into the pump housing? Think about this engineering problem for a second. How in the world do we connect a spinning motor to the pump without it shaking itself apart? We've got this massive, heavy motor spinning at thousands of revolutions per minute, and we need to safely bridge that raw power over to the liquid side. Imagine thousands of RPMs instantly torquing a static metal shaft. Without a proper bridge, the metal would literally shear itself apart in milliseconds. Well, right in the center, notice the coupling. It connects the motor's drive directly to the central pump shaft. It acts as a physical bridge over that gap, absorbing a tremendous amount of starting torque. And see that silver metal shield wrapping over it? That's the coupling guard, shielding those dangerously fast-spinning parts to prevent catastrophic accidents. It's a critical safety feature. Now, if you're ever on the floor and you hear a violent knocking or chattering sound coming from the center of the pump, this coupling is almost always the culprit. It means the alignment is off and it's tearing itself to pieces. Is everyone clear on how the power safely crosses over? Great. Let's keep following that energy. Section 4. Pumping action. Impeller and volute. Now that our shaft is successfully spinning and carrying that energy forward, let's actually look at where the work of moving the fluid happens. First up, the impeller. Think of this as the internal rotating component that's attached directly to the pump shaft. Its job is to push the fluid outward. The impeller is the true heart of the pump. It takes the rotational energy from the shaft and violently throws the liquid outward using immense centrifugal force. And I mean immense. The forces here are so extreme that if the fluid conditions aren't perfectly right, microscopic vapor bubbles can form and implode against the metal.
We call this cavitation, and it will literally eat away the solid metal impeller blades over time like a swarm of mechanical termites.
Next is the volute. This is the spiral-shaped casing that receives the fluid and helps guide it out. That high-speed liquid being thrown by the impeller is caught right here by the volute. Now, it isn't just some simple pipe. Its expanding spiral shape is specifically engineered to slow the fluid down just enough to efficiently convert all that wild, high-speed kinetic energy into usable, stable fluid pressure. Basically, it tames the chaos. Let's follow the path of the water together. Look over to the far left to see the inlet flange where liquid enters. The fluid travels straight in, directly hitting the eye of that silver impeller before being aggressively pushed outward through the expanding volute chamber, all contained safely inside that heavy blue pump casing. The kinetic energy is transformed into fluid pressure right here in this specific chamber. Are you seeing how that rotational energy translates into directional pressure? Awesome. We've officially moved the water. Okay, Section 5, Protection Components, Seals and Bearings. We've successfully moved the fluid, sure, but we have a major mechanical conflict we've got to resolve before our machine completely destroys itself. Consider this inherent problem. When a fast metal shaft spins inside a static metal casing full of pressurized liquid, how do we prevent leaks and friction? You can't just have a spinning metal rod rubbing against a static hole in a tank of water without something keeping the water in and the heat down. If you do, it's either going to leak like a sieve or just melt down from the raw friction. So look right where the shaft enters the casing. Here, we rely on the mechanical seal and the stuffing box packing to stop the bulk of the liquid from escaping. They are our ultimate barriers against the pressure. But look just below that. The seal drain safely catches any minor necessary seepage. And this is a huge point I want you to understand. Why is seepage necessary? Most people think any leak is a failure, but traditional packing actually requires a slow, steady drip of the fluid to cool the intense friction of that spinning shaft. Without that tiny intentional leak, the packing burns up, hardens, and destroys the shaft. The drain simply keeps the floor clean while this intended cooling process happens. Does that make sense? It's a controlled leak. And we absolutely cannot forget our unsung protective heroes. To keep that shaft perfectly aligned and spinning smoothly without grinding violently against the casing, we rely on critical support structures. We've got the outboard bearing and the bearing housing wrapping right around the shaft, and all of this is held up firmly by the support pedestal anchored to the base. Think about our failure tree. If these bearings fail, the shaft drops out of alignment. If the shaft drops, the impeller grinds against the inside of the casing and your pump is instantly destroyed. They might be small components, but they hold the life of the entire machine in their hands. Finally, Section 6, Mastering the Tree Troubleshooting Guide. Let's bring this all together and see how this step-by-step knowledge builds directly into your ability to troubleshoot like a pro. Here is the key takeaway. Every labeled component is a potential branch on the failure tree. Because we patiently walked through this step-by-step, you can now trace symptoms back to their source. If you walk by and see a massive puddle on the floor, it points straight to a failure of the seals or packing. If the pump is vibrating violently and shaking the pipes, check the impeller for imbalance or cavitation damage. If the machine is screaming with a high-pitched whine, your bearings are likely shot and need immediate replacement. And if there's a heavy clanking in the middle, check the coupling. See? You're no longer just guessing, you are diagnosing. Take a look at the complete system here one more time. By viewing this complex machine, not as a terrifying black box, but as a logical sequence of the motor, shaft, impeller, and seals, you have successfully mastered the very first step of failure analysis. You understand the what and where, which is absolutely essential for diagnosing the why. You've done the work, and the underlying logic of the machine is now completely clear. So, as your tutor, I'm going to leave you with one final test. Which of these components do you think is the most frequent culprit for catastrophic pump downtime? As you look at this diagram one last time, ask yourself which part bears the absolute most mechanical stress day in and day out. Figure that out and you will know exactly where a seasoned maintenance technician looks first. Think about it. Thanks for learning with me today.